So let's say that it is the mid to late 17th century, and you, Isaac Newton, are hanging out doing some math and trying to develop this new idea of the calculus. Um, and you are looking for different applications of things that you can do with this idea of the rate of change or the derivative. Okay, and one thing that you know is useful in math is being able to solve equations. All right, and you don't have, obviously, you don't have a TI-84 to help you out. Okay, you do have a counting machine. Counting machines did exist by this time. Pascal was one of the first people to develop one of these before Newton's time, and this was something that could like do computations even with some tedious numbers. So you could do computations. You could also graph something by hand, or at least get a decent idea of what a graph looked like, because you could plug numbers into a function and then plot those points. And again, it might be kind of tedious, but you do have the mathematical ability to do these things, okay? So anyway, let's say that you are trying to figure out how the derivative can help you with a basic problem in math, which is solving equations. So you come up with this process where you can start by approximating a solution to an equation, and then you look to see how the derivative can help you with that, okay? Now, again, you have the capability to get a general idea what the graph looks like. So the very first step in this method that you're developing is to just visually approximate what a solution is. Okay. Now for this one right here, this function that I have drawn, this is it appears that we're just a little bit to the right of 2. Now I'm going to start with a number that's further away from 2 so that we can visually see what's going on a little bit better. But the idea is you start by approximating what the solution is. So a decent approximation here would be like, let's start at x equals 2 or 2.1 or something like that. But again, for our purposes, I'm going to pick a different x. So let's say that you understand that picking one x value can allow you to find an ordered pair on your function. Okay, and so you know how to, any x value, you have this counting machine that will help you evaluate. So wherever x is, and we can start at different points, but again, I'm going to give us a little bit of space here. So you can take this x coordinate, which happens to be 3.73, and you can use your counting machine, you can plug it into this function, and you get a y value. Okay, now, the new thing that you can do, because you are developing derivatives and the process of linear approximation, remember we talked about that in 2.9 in the book, and what you can do is you can find the derivative of a function, and you can plug this x coordinate into your derivative function, and that's going to give you the slope of a tangent line. Well, if you have the slope of a tangent line and you have an ordered pair, you can write the equation for a tangent line. And this does have some kind of gross decimals in it, and which is not ideal, but remember, we're trying to develop some kind of way to solve an equation, and we're talking about equations that aren't like rational functions or polynomials necessarily, even not something that can nicely factor. Okay, so we have this tangent line now, and then if you have the equation of a line, you know that you can solve for an x-intercept. Because it's easy to solve an equation that's linear, where one coordinate is equal to 0, all right? So once you have the equation of this tangent line, you can pretty easily find the x-intercept, and we get this second point. Remember, that was kind of the point of linear approximation, was we use a tangent line and then find a point on the tangent line, because solving lines is much easier than any other type of function. So here we're doing the same thing, except the point that we're solving on that tangent line is always going to be the x-intercept, okay? All right, so once you have this x-intercept, you say, all right, well, now if I have a new x-coordinate, I can plug my new x-coordinate into my function and get a new ordered pair. All right, and then again, you have the derivative, so you can repeat the process of finding the equation of the tangent line through this new point on the function. Okay, and if you notice, we're getting a little bit closer. All right, so we can, once we have the equation of this new line, we can find the new x-intercept. Okay, new x-intercept means new ordered pair, take that x coordinate, plug it into the function, and then a new ordered pair means the equation of a new tangent line. And again, as you can see, we are getting closer and closer and closer to the actual solution. Okay, now, like I said before, I spaced this out so that we could better see what's going on, but realistically, you're going to start with a number that's really close. So watch what happens if we were to have started this with something that is close to our x-intercept. Okay, you see that if we would have started at 2, okay, we would have gotten to at least a decent approximation for our x-intercept pretty quickly. So what this does is it gives us a method for solving an equation, okay, because we can just take the equation, move everything to one side so that it's equal to 0, okay? So we can take that equation and then we can use this process of repeatedly finding the an ordered pair and then a derivative and a tangent line and an x-intercept and then a new ordered pair, etc., where we repeat this algorithm of using linear approximations to find the approximate solution. And we can do this and get as close as we want. So we might have something that maybe we want to get within 7 decimal places. We can do that using this method. Okay? Now, are we going to do this by hand? No, we are not. Are we going to take advantage of the technology that is available to us and use our graphing calculators? Yes, we are. Okay? But I want you to see this visualization of the process and understand how even in pre-electronic times, Isaac Newton was able to use something basic like a derivative and equations of a line to come up with a method for solving. So that's the background of how this process works and what it looks like and why it was developed. In video part 2, I'm going to go through a process for rearranging algebraically so that we can get our calculators to do this for us very quickly.